Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Richard Jacobs with the Finding Genius Podcast. My guest is from MIT. He's an associate professor. His name is Asegun Henry. So, Professor Henry, or maybe I should call you Asegun, thanks for coming.
Thank you for having me.
Yeah, well, we're going to talk about your research. So, if you would, can you just state it in your own terms? What's your research about?
So my research really centers on heat transfer and energy. My research group and the topics that we work on are a bit self-segregated into two separate areas. On the one side, we do like fundamental science work on the fundamental physics of heat transfer. We study heat transfer at the atomic level by looking at how atoms move, how atoms vibrate, and we develop, theoretical models, approaches, frameworks for understanding heat transfer and the physics of heat transfer in that context. The other half of my work is more large scale, relevant for, essentially we're interested in any technology that can move the needle on climate change. But our expertise is specifically in heat transfer, and we have a tendency to really work specifically on technologies that involve heat transfer at high temperatures. That's really where our core expertise is. So we build and test prototypes and technologies that have some ability to reduce greenhouse gas emissions. There are two main technologies that we're working on right now. The first is an energy storage technology that involves storing heat as opposed to electricity directly in order to achieve extremely low costs. And the second is a technology that would be used for hydrogen production. And current hydrogen production actually puts out a bunch of CO2. And so this would be an approach to making CO2-free hydrogen.
This is great. There's a lot to talk about. I'm always thinking about heat and cold, I think, because I'm always hot and sweating. So it's very important for me to stay cool. Yes, I wanted to ask you first on the underlying physics side. If I have a pot of water and I heat it, how is that actually happening? If you can go into like the basic physics of it, like what's literally happening when you want to heat something up?
Yeah, it's a great question. This question, I think, in the way you're asking it, is a big part of what led me into this field, is because I had the same question, and it took a while before I felt like I could get a straight answer on what it is. Because I used to ask, well, what is temperature, and why does temperature have its own units? But basically what is happening, every object, including yourself, and every object around you, including the air, everything consists of atoms, and those atoms are constantly in motion. They're constantly moving around. And so what temperature is it is a measure of the average kinetic energy of the atoms. Kinetic energy is 1/2 mass times velocity squared. So it's essentially a measure of the speed of the atoms and how quickly they're moving. When you have something like a solid, the atoms are generally fixed to a particular location. An individual atom moves around a specific site or location, but it'll move back and forth and vibrate around that site, but it doesn't go away from that. And so what happens is then you can think of those vibrations as consisting of a variety of different frequencies. So there's lots of frequency components and content to those vibrations. What happens is that the frequency spectrum, or the frequency content of a particular material, is not so much temperature dependent. It doesn't really change much with temperature. But what does change with temperature is the amplitude of the vibration. So the vibrations get larger, they move further away from that central location that they vibrate around. And so what happens is, as something heats up, the molecules are essentially moving faster. There's a faster speed. You asked this question about water. In the case of a liquid, what makes a liquid is that those atoms are not restricted to vibrating about a particular fixed location in space or fixed location within the material. Instead, they can diffuse around, they can move around in that local, they could do vibrations, but then the local position that they're vibrating around is changing in time, and then they're drifting and moving about throughout the material. So in the case of liquid water, what's happening is, again, the vibrations are, the speed of the vibrations of the velocities are increasing as you heat it up, but the atoms are able to move around and diffuse around in addition to vibrating at the same time.
So I have a question about solids. So if something's in a matrix and it can vibrate, at some point, wouldn't it have an average velocity of 0? It seems like it would go to one side and stretch the matrix that it's in, and then go to like a 0 velocity for a second, and then come back and pass through a maximum. And
that's exactly correct. Yes. So the average velocity in terms of the vector, in terms of what direction it points, is 0, because they vibrate around a central location, and if you measure it relative to that, it's 0. But the speed, but what the kinetic energy is 1/2 times mass times velocity squared. The square of the velocity is not 0. So the square of the velocity will always be positive, and so the average of the square will be some positive number.
But if you heat up a solid versus a liquid or a gas, I would think you'd have different heating characteristics, different curves, different ways that it changes temperature.
Yes and no. Yes, in the sense that there's a key property of a material called its thermal conductivity, that is the measure of how well a material can conduct heat, can move heat through it. More specifically, to get a little bit more technical, what the thermal conductivity is it's the proportionality constant between the rate at which heat is flowing through, or energy is flowing through a material as it's conducting heat, and the corresponding temperature gradient in the material, meaning how steeply or how quickly the temperature is changing from one location to another. So the thermal conductivity is probably the most important key property that would affect what you're saying, which is the temperature profile, or how the temperature evolves in a material. But there's a second aspect to it as well. Specifically, if you're talking about a fluid, fluids can move around. And so, even though you have, let's say, water in a pot, the water, in its bulk sense, it can be stationary inside the pot. It's not moving. It's not going to come out of the pot. But internally, if you were to image it, if you put like food coloring in it and you start heating it, you'll see the food coloring start to stir itself. You'll see internally the water is actually moving. And those are what we call convection currents, or natural convection currents. They're driven by buoyancy within the water. So in short, I would say solids, you can have a characteristic curve or a characteristic response to a thermal perturbation or a thermal heating event in some respect. And it's dictated by its material properties, its thermal conductivity, its density, its heat capacity. There's several thermal properties that dictate how it responds, but you can non-dimensionalize the problem such that all responses collapse onto one particular solution to the problem. And a similar thing can happen for fluids, which include both liquids and gases, which now accounts for two aspects, which is the thermal conduction, but also the potential for the fluid to move at the same time. And so these things we're talking about are, the main undertakings in the courses that I teach, where we talk about these things and students learn how to model them.
Yeah, and if you wouldn't mind, one more question about it.
Sure.
So if I just have two atoms, one has a certain kinetic energy, another one has another, and how does energy transfer or heating occur between them? Is it only by collision? Are there other ways that heat is transferred?
Excellent question. So it is not only by collision. So, for example, in a solid, you could argue that the atoms never really, quote unquote, collide per se. They are spaced out in a way that they are sitting in a energetic well or a potential well where each one is in effect trapped in a local region of space. And that's why they vibrate around one central location. And it's because they'd like to escape and go somewhere else, except the atoms around them push and pull on them, keeping them trapped in a particular cage. And then all the atoms feel that type of cage. And where these forces come from is that each atom is comprised of protons, electrons, and neutrons. Protons and electrons specifically have charge. And so charged particles exert forces, Coulombic forces, on each other. And so the substituent particles that are inside of an atom are what end up exerting forces on neighboring atoms. These effects or these forces are somewhat screened by the surrounding electrons and other particles and atoms that exist. But in the end, atoms exert forces on each other. And my group in particular spends a lot of effort trying to actually model these kinds of interactions and develop models to describe these kinds of forces, because these forces dictate the dynamics of how the atoms move, and that ultimately dictates the heat transfer. So that's one of the main ways that heat is transferred, is through these pulling and pushing forces between atoms. But the energy can also be transferred from one location to another via electrons. So an electron can, for example, be excited to a higher state, move through the material, interact with the surrounding atoms in a different location, and, so to speak, deposit the energy that it was energized with from another location. And similarly, another thing that can happen is photons within a material can also move energy. So you can have electromagnetic waves that carry energy from a region of the material where the atoms have higher speeds to another region where they have lower speed. So all three of those are potential mechanisms at the atomic level for how energy can move.
So I guess if you allow or restrict or try to stick to one mode of heating, you could probably get very different effects.
Yeah, so what generally happens is the extent to which any of those three mechanisms are at play depends on the type of material and also the temperature of the material. So the first one I mentioned, where the atoms are interacting, that is always at play in all materials. It's always there. That's there, as you approach absolute zero. It's the one that never goes away. The electrons are generally most significant for metals, where they have lots of electrons that can move around freely. That's where that effect is most significant. Or if you have another material that maybe isn't a metal at moderate temperatures, but if you heat it up really hot, it starts to become electrically conducting, then the electrons can become significant. And similarly for photons, they are often negligible at lower temperatures, moderate temperatures. But if you get to extremely high temperatures, which is something that we deal with in my research group, you get well above 1000 C or so, and the photon component of these things of heat transfer becomes very non-negligible, because radiation, thermal radiation, which is essentially the emitting and absorption and transfer of photons via thermal energy, that the emission of photons, or the rate of emission of photons, scales with temperature to the fourth power. So it's very fast increase in the amount of photons that are coming out as you heat up a material.
Oh, so that could become the predominant method of heat transfer in higher temperature systems.
Exactly, yeah. When you get really hot, the photons dominate.
Oh, okay. So you mentioned, I hope I get this right, you said you have a way of, of accomplishing heating or cooling, or at least storing heat instead of storing something else. Could you recap what you meant? Talk about that part of your research.
Yeah, there's a technology that we're developing. It's been affectionately called sun in a box. A colleague of mine called it that because we are working on storing energy at extremely high temperatures, higher than any other application I'm aware of that's commercially available. So what we're doing here is taking in electricity that could be excess electricity on the grid from really any source. It could be fossil, could be nuclear, renewable. In our case, we're most interested in storing, of course, renewable energy, and take that energy in the form of electricity and store it as heat. So you do that by using the electricity to run resistive heaters like Joule heating. And in doing that Joule heating, you now are converting electricity to heat, store that heat in a medium, like a very cheap material, such as liquid silicon or iron or even carbon or coal or something like that is very cheap, something that's very, very inexpensive. And you store the energy in that kinetic energy of the atoms. And those atoms are moving really fast, and you use that energy to heat them up. So you take them from one state of kinetic energy to a higher state, and that's where the energy is now stored. You generally store this energy in a system that is extremely large. So you need the size of the storage tanks to be order 10 meters in diameter, order 10 meters tall. So there's like typically tens of thousands of tons of material inside that's hot. And the typical way to do this is with what's called two-tank thermal storage, where you have a quote-unquote cold tank and another tank that's quote-unquote hot tank. In this case, in this technology, we're interested in storing the energy in liquid silicon. So you take colder liquid silicon. Here I'm using the term colder, but it's actually cold here is extremely hot to begin with. So the cold silicon is at 1900 degrees C, which is already glowing white hot. You take electricity and heat that silicon up to 2400 degrees C, so even hotter, more glowing white hot. And because the tanks are large, that silicon would take an extremely long amount of time to cool down, like on the order of months. So you use a very large size tank in order to reduce the amount of heat leakage you get to the environment. The whole tank's insulated, so you try to prevent the heat from getting out, but it will inevitably get out gradually, but you slow the time scale so that you'd lose very little over the course of the day where you would cycle this battery.
And the quality of the heat is high enough that it can be used for a lot of applications.
Well, yeah, we want to convert it back to electricity and put it back on the grid later when the grid demands it. And so, in essence, this system behaves just like a battery. You put in electricity, and electricity comes back out later. It's just that we're storing it intermediately as heat rather than electricity. And in doing so, we're able to drop the cost dramatically.
Can you do this on a small scale for electronic devices that normally would have, or maybe even a car that normally would have heat loss, and create like a small cladded or insulated area on a car or a machine or somewhere in that electricity is being used, and have a little battery that can give power back when needed?
Yeah, I mean, in short, the short answer is not really. You could do it. It's just extremely inefficient to do it when it's small. So the efficiency of the system scales strongly, at least when it's small. It's very strongly impacted by the size. Eventually, you make it big enough, and eventually the size doesn't really matter. And what this comes down to is what we call the surface area to volume ratio. The rate at which the energy is able to leak out to the environment from the storage unit scales with the amount of surface area that's exposed to the environment, which is like the outer surface area of the battery, like whatever its container is. On the other hand, the amount of energy that you're storing scales with the volume inside the container. And so if you take the ratio of those two things, the surface area to volume ratio, the ratio is much larger when an object is small. The amount of area you have to the amount of volume is a much larger number when it's small. And so when things are small, the heat losses are very significant, and they detract from your ability to store the energy. So case in point, maybe I'll give you a simple, easy example. Imagine the amount of surface area and volume associated with a cup of coffee. So if you put a cup of coffee on your desk, the time it will take to cool down is, it'll be much cooler, noticeably cooler over the course of 30 minutes to an hour. However, if that cup of coffee was much larger, let's say the exact same aspect ratio, it's still a cup, it looks just like a cup, but now imagine you've made it so large that there's 10 gallons of coffee inside. The amount of time it would take that coffee to cool down would probably be more like 10 hours, right? So the amount of time it takes something to cool down is affected by this surface area to volume ratio. So the idea in this technology, which it's a well-established idea because there's another technology that uses this same principle commercially and it works quite well, which is called concentrated solar power. The idea is that you make the system large, so large that the time it would take to cool down in any significant way is much longer than one day. And therefore, when you store energy this way, if you charge the system in the morning, discharge it the next morning, the amount of energy you've lost as compared to how much you had stored is a small fraction, less than like 1% of the total amount of energy. So it's a small
for solar applications like diurnal, that's perfect, because you really only need maybe 12 hours at most of storage.
Exactly. Yeah. So there's two time scales to be aware of. There's how long the energy can sit unused and to what extent it degrades over time just sitting without being used. That's one time scale. That in general for thermal energy storage, when you make it nice and large, is on the order of like a month or more. There's a separate issue, which is then how much energy you have stored and how long you can discharge your battery, which is a separate time, which could be targeted, like you said, for like 12 hours, where you might charge up your battery and expect to discharge it for all 12 hours of nighttime.
What the insulation of the container that this liquid silicon goes into, what if, so if, let's say I'm sitting inside the container looking around, the surface, I'll see the interior surface, is it very smooth? Or does it matter if that's like very, wrinkled and has a lot of surface area exposing, me, the silicon, to the cladding? Can the insulation be good enough that, could you create, let's say, a smaller geometry one where you have like it looks like a wire of silicon, but it's liquid, a channel like snakes back and forth, back and forth, back and forth within a volume. So there's a lot of, liquid that can be put in there, let's say, but it has a lot of surface area, but it's exposed to the insulation, and maybe the heat won't go out. I don't know.
So what you would want to do in this case is, I think, the reverse of what you're saying. You actually want to minimize the amount of surface area. So the amount of heat loss you get is proportional to the surface area. So if anything, you want to minimize the amount of. And the second thing is, what largely dictates the amount of heat leakage is the insulation on the outside. So even if you did have something like you said, where maybe the inside of the tank was very rough and you have some surface area enhancement because of the tank wall, it wouldn't matter much at all, because the main thing blocking the heat from getting out is something behind that element, which would be the insulation. The insulation is where most of the temperature gradient will occur, where the temperature decrease will happen. So in essence, the entire tank could be effectively isothermal. It could all be one temperature, and it won't really make much difference.
So I guess the quality or the qualities of the liquid are probably very important. I guess ideally it would be a very viscous liquid that has low heat transfer in it.
Yeah, so that's one of the reasons we've been interested in silicon. Silicon, along with most liquid metals, has a low viscosity right after melting. So most liquid metals have a viscosity similar to that of water. So they pour very easily, just like water, and they flow just like water. Silicon is similar to that. The benefit, though, of liquid metals is that they have very, very high thermal conductivities as compared to essentially all other liquid. Their thermal conductivities can be 100 or 1,000 times larger than something like water. And because of that, the amount of heat transfer, the heat transfer rate you get when you pump them is extremely high. So high that it essentially is usually not the limiting resistance or the limiting factor in transferring heat.
So what kind of commercial applications is your system perfect for?
So the main one we're targeting is energy storage, as I mentioned. Our approach to doing energy storage here is, again, to store energy in a medium at a very high temperature, nominally from 1900 degrees C up to 2400 degrees C. And then what I didn't mention is then you pump that liquid and you transfer heat to a heat engine to convert it back to electricity later. Here, what's, I think, a big departure for us as compared to other approaches previously is we actually use photovoltaics as the heat engine. So because the entire infrastructure is glowing white hot, we actually use specially designed photovoltaic panels to do the conversion of the light back to electricity. And these PV cells are very unique in the sense that they have mirrors on the back of them, so that any light that we do not convert, we try to send it right back to the infrastructure so it's reabsorbed and not wasted. This is where this term sun in a box came from, is the idea that you've effectively trapped your heat source inside of a box so the light is not able to get out and get wasted.
If you ever burn yourself on one of these, you can say, son of a box.
That's a good one. But no. Generally speaking, these things are so hot that you can't even really look at it directly. You have to have the insulation around it to get it that hot in the first place. And these things are shrouded around as well with an external containment system of like a steel box or steel container or vacuum chamber around it. All these things, the vacuum chamber, if you touch the outside of it, feels like it's at room temperature. So the vacuum chamber doesn't heat.
Oh, wow.
So the temperature decreases a lot as you go away from the central portion that's really extremely hot.
So what kind of efficiencies can you get from this? And when you add it onto a system, how much more efficient does it make it?
So our target is to get to about 50% efficiency, meaning for all the electricity you put in, you get about 50% of the electricity back when you discharge it. And so that's actually quite low compared to other technologies like batteries or pumped hydro. What is the selling point, though, is that economically, when we write it down on paper, at least it appears that our technology would win on cost despite the low efficiency, because the cost of storing the energy is like a factor of 20 to 100 lower than batteries or pump or other technology, right? So we end up winning on cost because we do pay a penalty on efficiency. Our efficiency is lower, but at the same time, our cost is much lower. It's a bigger improvement on cost than efficiency, and it outweighs in the end.
Huh. Is there any difference in the quality of the heat that you get, or the quality of the electricity that you get out of this versus other power systems? Are there certain ones that it's more amenable to and ones that it's not useful for?
The quality of the electricity is essentially the same as anything else. The quality of the heat is dramatically different. So this is, extremely high quality heat that we're using. That's part of the reason we're going to such high temperatures in the first place, is to try and maximize the exergy and minimize thermodynamically how much entropy we put into the system.
So for certain applications, if you need to boil something, if you need to heat something up, would you need to convert this back to electricity? I mean, a lot of industrial systems are, produce heat, let's say boil water, and that turns a turbine. Could you use this without going back to electricity to accomplish the same thing in a plant?
You could, in theory. My suspicion is that there are a number of other approaches one would use if the temperatures at which you're going to use the heat are much lower. Then there's really no need to go as hot as we're going. You could use a variety of other media and do it a variety of other ways that would be easier to implement and possibly cheaper. This approach we've designed is specifically focused on having electricity as the output, and that's why we go to such an extreme temperature.
Okay. And the other application you spoke about in terms of green energy, what's your research look like there?
So that's a project that we actually just got some support for recently, and we're very excited about it. To understand it, it's probably good to understand the state of the art. So the way hydrogen is made today is through a process called steam methane reforming, which often typically involves a second reaction called the water gas shift reaction. So how this works is the desire is to make hydrogen, H2. So what you start with is methane, which is CH4. So it's got 4 hydrogen atoms on it and 1 carbon. And you normally react it with water. Water's got 2 hydrogens and 1 oxygen. And when water reacts with methane, it'll form carbon monoxide, and all those hydrogens will come off and separately form hydrogen. So you'll get a bunch of hydrogen out and you'll form carbon monoxide. The water gas shift reaction is then the second reaction, where you then take the carbon monoxide out and react it with more water to form carbon dioxide, which can now go out into the atmosphere, although it's a pollutant and causes global warming. But you can make CO2 and a little bit more hydrogen. So this process is really important because we primarily use hydrogen to make ammonia and ammonia to make fertilizer, so that we can make food for almost 8 billion people on Earth. So it's an absolutely vital part of human existence, this approach, this process. Problem is it makes, it's responsible for about 1% or so of CO2 emissions globally. And so instead, our approach is to still take the same input of methane, but instead to do something different, which is, since we've now developed this approach to flow liquid metals at extremely high temperatures, we instead take the methane and heat it up to a very high temperature, about 1400 degrees C, not as hot as the energy storage, but still glowing white hot. And around 1400 degrees C, methane will decompose on its own thermally. It will do what's called pyrolysis. It'll pyrolyze into solid carbon and gaseous hydrogen. So the hydrogen will come off on its own and leave behind solid carbon rather than making CO2. The reason that's really valuable is because solid carbon is much more valuable as a product than carbon dioxide is. Carbon dioxide, we have an overabundance of it, and we're trying to figure out how to get it concentrate it and put it under the ground or sequester it or put it somewhere so that it doesn't cause global warming. But solid carbon doesn't, of course, go into the atmosphere and could presumably be used for something else. Our vision is to take the solid carbon we make in the reactor and turn it into a construction material so that you can actually make something that would displace cement, which cement is responsible for about 10% of global CO2 emissions. So we'd like to essentially solve two problems with one technology and minimize, cut CO2 emissions by up to about 11% if we can do both industries with this approach. The problem with doing it sounds simple and straightforward, but it's not. The simplest thing you could imagine doing is, okay, well, I'll just take a pipe, heat it up to 1400 degrees C and flow methane through it. So the methane will heat up to 1400 degrees C. When that happens, the reaction will take place. It will decompose. The problem is that solid carbon is just going to deposit on the walls of the tube. And so the solid carbon will build up very quickly and actually block the entire cross-section of the tube so you can't flow the methane through anymore. And so it'll plug itself. This is what we call the plugging problem. And so this problem's been around for a long time. And partly for this reason, this technology has never really taken off because of the plugging problem. So there's a group in Germany, Thomas Wetzel's group, that has demonstrated an alternative approach that solves the plugging problem, which is really nice. And the idea is to use an intermediate liquid as the means of delivering the heat to the gas. So instead of using a pipe wall, which is solid, to transfer energy to the methane gas, instead put a column, a large, let's say a vat or big chamber of liquid metal. The liquid metal here of choice is liquid tin, which is mostly what's used in solder. Liquid tin is special in this regard because liquid tin, very surprisingly, has no chemical interaction with carbon or hydrogen. It's actually inert with respect to carbon and hydrogen. So liquid tin can sit in this, large container. You heat the liquid tin up to 1400 degrees C, and now what you do is blow methane bubbles up from the bottom. So as the bubbles rise, they will heat up to this 1400 degrees C. The reaction will carry out inside the bubble, and now when the bubble reaches the surface of the liquid tin, the hydrogen will continue rising, and the carbon will float on top of the liquid tin. So you get a little carbon particle that'll sit on top of the tin. And so if you blow lots of bubbles, you'll build up a whole bed of carbon powder that floats on top of the liquid tin. The beauty of that is then you can now use the liquid tin to flow and move the carbon out in a continuous manner and make a continuous reactor that continually purges and pulls out carbon as you bubble in methane.
That's really cool. And what can you do with the carbon? What are some of the applications?
The biggest one, well, the main type of carbon that reactors of this nature seem to make is called carbon black. And there is a carbon black market today. It's primarily used in tires and in inks to make black ink. However, if you were to imagine that this process was successful, let me just say, if one would first sell to the carbon black market and make as much money as you can, carbon black sells from probably anywhere from, I believe, about $500 a ton to $2,000 a ton, depending upon the quality and its characteristics. What we are interested in, though, is taking the carbon black and turning it into a construction material. Particularly if you think about imagining this process being extremely successful, if it was to actually displace the current approach for making hydrogen, if that were to work and you now meet global hydrogen demand with this process and look at how much carbon you're going to make, you would quickly overrun the carbon black market. So all carbon black in that market would be saturated, and you'd have 10 times more carbon laying around that needs to go somewhere. This is why we've specifically focused on the construction market, looking to create a construction material that could rival cement. And in doing so, cement production would be a sufficiently large uptake for all this carbon. So the cement market is a factor of 10 larger than the amount of carbon we make. So it's big enough to take over.
Oh, so you can mix in, powdered carbon into cement and, alter its properties, but they still be desirable?
No, actually, the idea would be to make a completely new material that's mostly, almost entirely carbon. It replaces cement. Like, you don't even use cement anymore to make buildings. You use this carbon. It's carbon-based building.
Oh, interesting. What kind of, has anyone made a beam of it or, a pad of it? And what kind of properties does it have? It must be interesting.
Yeah, they have actually. I have a collaborator that I'm trying to work with. He shared some data with me and showed that he had actually made something that was 94% carbon. He added basically a binder, which is essentially like a glue to it, and he was able to make something that was stronger than not just concrete, but steel reinforced concrete. And so he could turn carbon into something that was stronger than steel and steel reinforced concrete.
I guess it's like a dirty diamond in a way in terms of its material properties, right?
Honestly, the most surprising thing with it is he actually showed a video demonstrating that it's actually fire retardant. So he tried to set it on fire with a torch and it doesn't catch fire.
It makes sense. Yeah, there's no, oxygens or hydrogens or anything attached to it. Yeah.
Well, there's the oxygen in the air, but it doesn't really have enough surface area to really catch on fire, to get hot enough to catch on fire. That I thought was particularly interesting because that means it could be used for homes and very large building structures as a cement replacement. Because my understanding is that one of the big criteria for using it in larger civil structures is it's got to be fire retardant.
Does it off gas, or like what other properties does it have that are interesting?
If it was to, it would oxidize. If you try to burn it, it will oxidize. It doesn't burn and catch fire, so you don't get a flame. But it will gradually oxidize if you heat it up hot enough. When it oxidizes, it's just making CO2.
That's weird. You could design a building, and if it got hot enough, the whole building just evaporates to nothing.
In a sense, yeah.
Weird. Huh. Well, very cool.
Thank you.
So, Asegun, what's the best way for people to learn more about the projects you're working on and see what your lab's doing? How can they get in touch?
Yeah, easiest way is to go to our website, which is ASE, first three letters of my name, ase.mit.edu. There's quite a bit of information and videos on the website to explain the things that we're working on. And I also have some activity on social media, Facebook, Instagram, just started with Twitter as well. Easy to find me, just Google my name, Asegun Henry, ASEGUN, last name Henry, HENRY.
That's great. Well, Asegun, thanks for coming on the podcast. It's been really cool to talk to you.
Thank you. Thank you for having me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.